Good morning, everyone. As we have seen the introduction of data analysis and visualization in last two sessions, let us see the basics of Python for data analysis and visualization, particularly for data analysis. You can observe, in order to perform data analysis, we need to handle a lot of numerical data and apply various statistical and probability techniques to find the insights to take a decision on data. So I'm using Anaconda Navigator's Jupyter Notebook platform to implement the Python libraries for data analysis. Of course, you can also use Google Colab without installing any software. Having a simple Gmail account is enough for you to just log into Gmail account and then go for Google Colab and then use. It has its own advantages. But as I am using here Jupyter Notebook and my local host, where you need an internet or the cloud services for the Google Colab. I don't require anything, an internet or anything for me to practice the applications of Python using Jupyter Notebook. Right, this is an interactive Python environment where I'm just using this on my local host, my own system. And coming to the basics for data analysis in Python, we'll start with Numpys. So I spoke about the basics of Python in another video. You can just reach out to the any of my other videos for basics of Python and then essential parts of the Python, like data types, functions, okay, operations, and then indexing, slicing. All these can be learned from my other videos. So let us focus on the major basics essential for data analysis in this session. As I provided in the contents, the basics of NumPy are very much important. The NumPy is a fundamental package for scientific computing with the Python. It contains, among the other things, like a powerful n-dimensional array object, a sophisticated broadcasting functions available in NumPy, tools for integrating C or C++ and Fortran code, and useful for linear algebra, Fourier transforms, and the random number capabilities. This has many advantages in NumPy. Particularly, in NumPy, we use to create arrays, multidimensional arrays, and applying the operations on the elements of arrays to find the insights. And the name of the library is NumPy. You can simply import the NumPy library by a simple code snippet. You can observe, if you get an error while running the above cell, import it by using the following command, or you can simply go to navigator and then environment. There you can simply pip install NumPy. So it comes with a basic libraries, and you don't need to install anything. But if this version doesn't support, you have to explicitly import them or install. Now to check with the version of NumPy, which I'm using in my interactive notebook, you can simply use np is an alias name of the NumPy library, np dot hyphen version hyphen. So the version which I'm using in this interactive environment is 1.24.3, but now most of us are using 3.3 and above versions, and there is no much difference between these versions, but you have got a lot many features in the latest versions. Now, what I do is I just wanted to create an array and passing a list as an argument to array constructor through np library. And simply you see, so if I use a simply if I use 1, 4, 2, 5, 3, it's normally a list, right? It's normally a list. Whereas if you provide this list as an argument to an array, then it becomes an array. There's a lot of difference between a list and arrays. A list is a collection of heterogeneous values, whereas array is a collection of homogeneous values. It doesn't permit a different type values into a collection. So that is the basic difference. And then whereas handling the multi-dimensional lists is quite difficult, whereas arrays is a bit easy as it comes with the predefined structures through Numpy library. If you wanted to see, you can just see it, and then you can print a list and print array A. See the difference between the list. The items are separated like 1, 4, 2, 5, and 3, whereas it's a one object. It's one object. When it becomes an array, it's one object, right? Okay. So now you see, suppose if I try this, what happened? This is purely a list, not an array. It's purely a list. Okay. Let us see the differences between the array and the list. The data should be the same in all the elements in a NumPy array, whereas it can be different in case of list. And broadcasting will be supported by your NumPy. We will see the broadcasting in the end of this module. Yeah, we add an element of a string data type and a NumPy array, then it will upcast the data type to string of all the elements. See, this is one of the very important thing we need to observe. So when you have a heterogeneous values into a collection and you want it to convert into an array, which is very much difficult, because here you can observe you have integer values, you have a string, and you also have a boolean. Now we will create one sample thing. You can simply observe the output. So now you can see all of them are converted into a string. So this is what is called upcasting. Usually when you have different types into a list as an argument to an array, and then you try to convert all of them into upper data type, and then make it a uniform data type values. Now you can see here, and everything become a string. Now we will create one sample list and NumPy array and apply a very basic function of multiplication by 2. We'll see that in case of list, the elements are duplicated but append to the list, whereas in case of NumPy array, we got an array where all elements are multiplied by 2. Yeah, you can see, this is a simple list. If I multiply, what happened, you see. This multiplication is not the multiplication of the elements. It is the multiplication of the list. Now you can see this is actually a list, whereas it is multiplied into two lists. Okay. Whereas in arrays, you can multiply the scalar value. Okay. Now what I did is I have created a simple array. I've created my own array. If you want, you can observe. This is my array. If I multiply or add, what happen? If I add a scalar value 2 is added to every element of an array. That's how it becomes 1 become 3, 2 plus 4, 2 is 4, 3 plus 2 is 5, and so on and so forth. Right? So this is the major difference when you apply arithmetic operations on list and arrays. Create a matrix using NumPy. Simply how you can create the same way how you created multi-dimensional list is the same way you can create it. But initially I am just creating a list. This is basically a list now. It's not an array. Now I wanted to convert it to an array by passing this list as an argument. Then now you can see now I have got an array. So this becomes an array with an NumPy definition, and you can also access them. You can access them using their indexes. Now you see this is in the first row and the second column, where you all know the index starts from 0 and set the n-1. The row or column so always start from 0 and goes up to n-1 index position. So we will see how we will use this indexing and then slicing to access the elements of an array. Okay. And now you can create your own other array and let us perform different operations on it. Right. So let's create a 3 by 3 matrix by generating random numbers between 0 to 10. So here random is a function which creates a random integer in the given range. So 0 to 10, which indicates 0 is in always lower bound is inclusive and then upper bound is exclusive. That means it starts from 0 and ends at 9. Any random number will be picked for every iteration. So the size we gave is 3 into 3 is 9. So it's matched. Okay. Now the expected output is a 3 by 3 matrix. Okay. You have got all the random numbers in between 0 to 10. Right? 0 to 10, that is up to 9. And in 3 by 3 matrix form. Okay. So we can also create another matrix. So like this, you can create anything. Now you observe the elements of the first one and then second one are completely different, though the code snippet is same. You can observe the code snippet is np.random.randint, the range from 0 to 10, and then the shape or the size is 3 into 3. So I've got this two-dimensional array, whereas I use the same once again, but I got a different value. So this is because you are generating random. To fix this, we'll use a function called as a seed. We got a different matrix when we generated another random matrix. We get the same matrix again by fixing the seed. So if we use a seed will help us to set the starting value of the fixing the random seed. So if I probably see wherever you see, you'll see only 0 and 42 are the standard numbers that we use. But if you don't have a 42 as a range, then it by default it takes a 0. Okay, so what happen if you use the seed? Every time it generates the same collection. Now let us see. Now I got 503379352. So 9 random numbers have been generated by this random function. And as I use this seed 0, if I use it again, okay, if I run it again, I am supposed to get the same values. So without any change like the previous one. Now you can just take one more cell and then run it. You are supposed to get it. But where is your seed? The seed is missing. Okay? Seed is missing. Now you observe. So when I said the seed is always same, then you will get the same values though you repeat the code snippet. Got it? So this is very much important when you wanted to generate random values, and then random values are supposed to be the same for every iteration. Now you can say thought from also I just executed the same by setting up the seed is 0, then I got the same. So this is a one way how we can fix the problem of generating random values every time and new random values using NumPy, right? So you can also create a matrix of zeros of specific dimension. Sometimes we wanted to create arrays initializing with the zeros. Then we can simply use a function called zeros function with a dimension that you require, and then also data type. Okay, I told you the data type is very much important since all the values are supposed to be same type. Now you can see the create teaser array filled with the zeros. Now here I am using this is what 3 by 4. Now you can observe 3 rows and then 4 columns each. Okay, so all are filled with the zeros. Now, all right, you can create one more. So it's as you like. You can also create a 3-dimensional. It is applied in 1 dimension, 2 dimension, 3 dimension. That dimension is your choice. Okay? We call it as a size. So similar to that, you can also create a matrix of any size with all filled with ones. Filled with ones. Now you can see I just created a matrix of 2 into 10 size, and with all elements filled with 0. So usually this will help us to initialize the values. For suppose not only these zeros or ones, so if I wanted to fill a particular value into every position of an array, you can also do that using another function called a fill. We will see now. Now you can see. Now before that, we'll see you can also create an identity matrix where all the diagonal elements are 1. Okay, all the diagonal position elements are 1. Then it's always an identity matrix. So identity matrices are very much useful when you are doing multiplication because it will preserve the original values of a matrix which is being multiplied with an identity matrix. So to create a matrix of filled with any specific number, and then we can use a function called full. Now you can see if I wanted to create a matrix of size 3 into 5, where every element is supposed to be 3.14, which is a pi. Usually we call it a pi, right? So pi value. Okay. So then we can simply see now this is a simple half an array of all the elements are of 3.14 with a shape 3 into 5 matrix, right? And similar to that, if you want any alternate number, you can just see I wanted to create 2 into 4 matrix, all elements filled with 7. So these are the basics how you can create a arrays. Now I just wanted to concatenate uh, different arrays, the concatenation of matrices. You can do that. I'm working with a 2-dimensional array now. Since 1-dimensional array is not much useful in storing the data like features and then objectives, we'll be mostly using 2-dimensional and 3-dimensional. Right, let me name it as a matrix 1 and then matrix 2. A matrix 1 which I created, either you can directly create by generating the random values, or if you have already know your own values, you can just use your own values as an argument to an array constructor. Then you'll get your own array. So I just named it as a matrix 1, and then I created another matrix. It starts from 7, 8, 9, 10, 11, 12. Now, if you wanted to combine them, there is a function called as a concatenate. Okay, so you can concatenate them either row wise or column wise. Right? If you wanted to concatenate them column wise, you are supposed to provide the axis is 0. So when the axis is 0, what happen, you will able to combine or concatenate your arrays row wise. Sorry, row wise. See, 0 indicates row and then 1 indicates column now. See here, so what I did is I just defined a new matrix. That's what matrix 1 to combine row wise. And now I have a function called concatenate. This is also universal function. So np.concatenate, where the first argument is the first array and the second argument is the second array, and then it is supposed to be axis is equal to 0. What happened, it combines row wise. Now can you expect the result of this? Okay, so one followed by the other. So 1 2 3 4 5 6 is a matrix 1, and then and becomes the next row wise is 7 8 9, and then 10 11 12 are the other matrix. So if I use axis as 1, what happened, it comes adjacent to it. It comes and adjacent to it. You can see if I use concatenate the axis equal to 1, it comes as an other column. Now you can see 1 2 3 4 5 1 2 3 4 5 6 is actually the matrix, and then you have 7 8 9, and then 10 11 12 is another one. So it becomes a new column wise. All these are concatenated. Okay, so this is how we just use. So now let us see the other one. Yeah, so now let us see the structured data and NumPy structured arrays. Well, often our data can be well represented by a homogeneous array of values, as we have discussed it. Sometimes this is not the case. Okay, so then how we will handle it? It's very important for us to handle such things. So, but before this, what I suggest, let us see a few more basics. Okay, before we come to the structured, right? So let us see this and the data types. We'll finish the data types and the fixed type arrays, and then we'll move on. So for effective data-driven science, and then the computation requires understanding how data is stored and manipulated. Okay. See, I don't want to waste much of the time on this stuff, which is not so important for the people who wanted to work on NumPy and particularly data science. So now we will directly go to it, and then you can see the Python list is more than just a list, as I told. And then what's the normal list? You all understand the normal list is a simply list of elements, but whereas it is an object. Okay, whereas it is an object. And let us focus on the fixed type arrays in Python. So Python often offers several different options for storing data in efficient fixed type data buffers. The built-in array module can be used to create dense array of a uniform type. Now I wanted to create an array. Okay. So now what I did is I just created a list and pass a list as an argument to my np.array. Then it becomes array. A1 is an array now. And then the list I've created the other one. Now you can observe when you wanted to specify, you can specify the particular type. So D stands for decimal, and all this become a float. Okay, all this becomes what? Float, right? Now you can simply observe this. There's an error. The name NP is not defined. So why is the NP is not defined? We have not imported it. You have to import num as NP. Okay, it works now. And now you can see. So your A1 is 0 to 9. It generated some values. These are not random. These are just a range between 0 to 10. By default, it takes a lower bound is 0 to the range function, and it goes up to n minus 1 is that is 9. Totally 10 values are generated. And then your array is what? I just took only these values. And then when I mentioned its type, fixed type is D, so all decimal. Okay, so if I provide I, what happen? Well, suppose if I have the values like dot 0, 0.5, and then 0.4, 0.2, and 0.0. If I mention it's an I, so what happened? Now you observe. There is the problem. Then float object cannot be interpreted as an integer, so because it's not able to round it off. So when you mention it's a fixed, you are supposed to fix it. As I told you, the upcast, it is, see, you're trying to do it at the lower cast, which is not possible. If you have a lesser the type values, then it will be automatically converted into upper. So whereas vice versa is not possible. Okay, so that's the reason why by mentioning as an integer, you're not supposed to provide the upper cast, I mean upper data type values, isn't it? Now, so as I mentioned, it's an integer I, then I am supposed to give only the integers as elements. Okay, and then you can create arrays from the list, which we have already seen. But of course, the data types, fixed data types are very much important, as I told you. So there is another way you can fix the data types. There are so many data types. We'll discuss about them. And then NP array of 1, 2, 3, 4 is a list of elements, and then all of them I wanted to say these elements are supposed to be float values. So then when I mention the upper data type, if they are lower the type, they will be upcast automatically. That's the advantage of Numpy library. Now what happened? All they become, I mean, 1.0, 2.0, 3.0, and so on. Okay. Now you observe. Nested list results in multi-dimensional arrays. Of course, you can create multi-dimensional list and then pass it as an argument, and then you can create multi-dimensional array. Creating arrays from scratch, so we have seen bit of them, right? So zeros we have seen. So this is the different way how we can create the multi-dimensional arrays. So initially we start with a single dimension and then move on to the upper dimension. There's a 2-dimensional and 3-dimension, the different types. So earlier I didn't mention you what type it is, but if you wanted to stick onto a particular type without casting, okay, without upcasting or the downcast, so you have to explicitly mention what is the D type. D type indicates the data type, okay? So if you mention it explicitly, then it will not permit any other type element into an array. Of course, the definition itself says that you cannot have any heterogeneous values. Okay. Now, this is the one which we have seen, but this is a little interesting here. So, creating an array of 5 values evenly spaced between 0 and 1. It's quite interesting now for you. So, there is a function called linear space a function that creates a set of elements in the given uh, lower bound and then upper bound in between with the same distance, right? So what I want to do is I wanted to create 10 elements between 0 and 1 with the equal distance or equal difference. So for which you have a function called linear space. You can directly use with the first one as a starting of the elements, whereas the one is an end of the element. Both are inclusive. And then where 10 indicates the number of elements you wanted to generate. But when I use a linear space, it creates these many number of 10 elements with an equal distance. Okay. Enough. You can also create uniformly distributed random values between 0 to 1 by specifying the size. The size is 3 into 3. I did not mention exactly what is the actually what is the range, like 0 comma 1. But by default, the random function will understand the range is from 0 to 1 only. Okay. Now you can observe I'm able to create 3 by 3 matrix. Our values drawn from 0 to 1. Now you can see these are not equidistant. Understand? So, but whereas linear space function, in space function gave you the elements of you required with an equal difference. But whereas a random doesn't. But it's created an array of size 3 into 3. Okay, now let us see how we can create an array of normally distributed normal values, random values. The mean 0 and standard deviation 1. So mean is is an average of the elements. Whereas the standard deviation is the what is the standard deviation? The square root of the differences between the mean and then the element. Okay, squared average of the mean and the actual elements. Okay, now what you can see is, as I told you, you can also mention the now. You can carefully observe what I used is normal. Okay, so this normal is nothing but normal distribution. All right, now you can see between 0 and 1, I wanted to create 9 elements with the shape of 3 into 3. Right, all the elements in this normal function is a normal distribution function. Okay, normal distribution function gives you the standard deviation of every element. Standard deviation of every element. Now you can also see the random integers in the interval 0 comma 10. Okay, with the size and type. You're always free to mention the size and type. Okay, as we are studying about the fixed type, it will be very useful you to fix it and then avoid the ambiguity. Okay, so the other function is I function. Particularly when you talk about the I function, it helps us to create the diagonal matrix, right? So 3 indicates what? 3 diagonals. Always it's a square matrix. We know the identity matrices are the square matrix. It depends upon the number of elements in the diagonal, right? The diagonal is a 3 ones, right? And then I got 3 by 3 matrix. Okay, if I provide it a 4, you can see it's a 4, right? It's a 5, it's a 5 by 5 matrix. So the diagonal matrix is always square matrix and with an into n size. The most important is the empty function, which actually creates uninitialized elements into an array, right? Basically, this uninitialization means, see, when you create an empty array with an empty function, it creates an array of the size which you want, but all the elements are drawn from the memory location. We don't know what is stored in that memory location. So the same data is been displayed here. So that is what is uninitialization. You never know, you'll get some garbage values from the memory. Okay, so you have a signature called empty. The first one indicates the shape. All right, the second one indicates the type that you wanted to store, and then order is C. C indicates a row wise, and then F indicates a column wise. Okay, and now you see you got some. These are the values which are drawn from those memory locations. These are uninitialized. That's what these are, uninitialized elements into an integer array. I do not mention it's an integer, but you can mention if you want d type is equal to int, you can mention. By default, it's a float. Yeah. If you ask the standard data types, as we know, there are so many data types and then different versions of it. I suggest you to just explore them in a python.org and see what are the data types and their ranges. A lot discussed much about these basic data types, the integers, a float, okay, and then complex numbers. These are the various data types that we use in our numerical calculations, right? Now let us continue. Let us continue to see the how we can create a simple arrays and then work on their attributes. Okay, so then you can observe here the Numpy array attributes, and then seed we have seen, and then randint. So if you just wanted to create 3 by 3 matrix, the random numbers generated between 1 to 10. So I've got this, and then the advantage of putting a seed is if I run it no again and again, I'll get the same. Okay, and now as I told you, this can be accessed, right? So for suppose if I wanted to create a 3-dimensional matrix, so what two 3 into 2 matrices. 3 into 2 is a 3 rows and 2 columns of size, and then we'll have a two such 2-dimensional matrices. So this is what is a dimension. I can say is a column and this is a row, and there are two such matrices. Then they are the one. Now you can observe this is our 3-dimensional matrix. Is a 1 2-dimensional and then other 2-dimensional, and it is a 3-dimensional matrix. Okay. Yeah. Now you see, I just wanted to create 1 dimension, 2 dimension, 3 dimensions so that you can easily see all the difference and the same page, and which is very much useful for you to easily understand how simple it is to create a 1 dimension, 2 dimension, and 3 dimension. Right. Now the other attributes. Let us see the other attributes very important for arrays, and then number of dimensions, and then shape indicates what? The number of rows and columns, or the how many, for suppose if it's a 3-dimension, it's a number of rows and columns of a 2-dimensional followed by how many such 2-dimensional matrices are there. So then it indicates a x3 is a 3-dimensional matrix, and the dimensions are 3, and then its shape is 3 into 4 into 5. I mean to say 4 into 5 are of 3, right? And the total elements, the size indicates the total number of elements into that matrix or array is 60. Okay, and then data type of this 2-dimensional is an int. If it is 3, you can see it's an int 32. All the elements are of integer 32 because we have used random number generation, random int. So it generates the random integers only. By default, they are int 32, 4 bytes length uh, numbers. And the next attribute is item size, and then number of bytes it reserves for storing. So the item sets, every item, every element of an array having its own size, that is a 4 bytes. All right. To know the size of every element, you can use item size attribute, and then to know the size of the entire matrix on array, you can use n bytes. Now here I got every integer is 4 bytes. That's what is int 32. 4 into 8 is the 32, and the total elements are 60. 60 into 4 are 240. Okay. And the most important, array indexing. Indexing will help us to locate elements navigating through rows and columns. Right? If you are familiar with the Python standard list indexing, indexing and NumPy will feel quite familiar and then same. And a one-dimensional array, the ith value always starts from 0. As I said, can be accessed by specifying the desired index in a square bracket, just as with the Python list. So there is no much difference, but when it goes to multi-dimensional, there is a slight difference in it. Okay, I have one-dimensional array x1, and then with the values, these are the values of my array. Now I wanted to access the first one is 5. If I give this one as a 4, if you want anything else, also you can. For suppose if I wanted to access the last one, okay, x1 of -1. So now you see the last one, minus indicates it starts from the reverse. It starts from the reverse, the last. Okay, and this is what is called negative indexing. Now you can see I can navigate the second-most element by specifying -2. All right. The multidimensional array items can be accessed using a symbol. See, if it's a multidimensional, what you use? Simply use a comma. Okay, I can simply use a comma. So as x2 is a two-dimensional, I wanted to access the element, what you say, this 1. And tell me, how can I access 1? 0, 1, 2. All right. Now, 0, 1, 2 is the third row and then first column. Okay. So if I wanted to access a 2, 2 is 0, 0, 2. Right. So like this, when you want, you can. You can also use negative indexing. You can also use negative indexing. Well, suppose if I use the -2 and 2 and then -1, what happened? -2. This is from here. It's -1, -2. This row, and then -1 from here. So this 80 is actually the element which is identified from rows is a -2 and column is -1. Okay, if I give 1, what happened? It starts from the beginning to second. So that's 6. All right. So like this, you can use negative indexing or no positive indexing to locate a particular element in an array. Could it be single dimensional or multi-dimensional? It is the same way how we use the indexing concept, but we simply separate the index positions using a comma. So if it's three-dimensional, we are supposed to provide 3 index positions. Okay, stating the first one is the highest dimension, second one is the lowermost, and then now the last one is the utmost, lowermost, the one. So values can be modified using, see, as we are able to locate to them, we can also change them. So simple assignment operator will assign the values that overlap. So this is a normal practice. If I wanted to change the element, let us see my, now let us see, this is our matrix. I just wanted to change some value. Let me say I wanted to change 7 into some 17. So what is that? X2 is my 1. How do I locate the 7? 0, 1. Okay, second row. And then column is 0. Right? Basically, this is what is 7. I wanted to change this. Okay, with some 20. Right? Now you can observe. If I use x2, now you can see my 7 is actually replaced with what? 70. So this is permanently saved. This is an assignment. You can modify the values like this. See, locating to a particular element always required what? The index position. Could it be one dimensional or two dimensional? And you'll separate with the commas when you are going on dimension to dimension, more dimensions. Okay. So that's how you will simply work with. And now this is what a simple time the indexing and then accessing the elements by locating a desired location of an array. So similar to that, slicing will help us to extract a part of an array called as a subarrays. Okay, just as we can use square brackets to access individual element arrays. Okay, individual array elements. We can also use them to access subarrays with the slice notation. So we use a colon as a slice notation, and the NumPy slicing syntax follows that one of the standard Python list. To access a slice of an array X, we use this syntax. This is the signature that we follow for slicing. First one is always the starting position of an array, and then next one is the ending position of an array, and then step means another. So after how many another elements you wanted to locate. So if any of these are unspecified, by default starting is treated as a 0 and then first position, and then stop is the size of the dimension. So very careful when I say size of the dimension is not the shape. Size of the dimension is earlier it is how many elements we have, 60, right? So similar to that. Okay, your step is always 1 because the 1 indicates the immediately one after one element followed by another element. Okay, so without skipping any element, if you wanted to navigate through all the elements, then step by default step is 1, next one. All right, so we will take a look at accessing these subarrays using a single dimensional or the multi-dimensional arrays. So when you go to one-dimensional array, and then we'll see how we can extract the subarrays. So now what I did is I just created an array of elements between 0 to 10 elements, and then I wanted to extract 5. And then how do you slice it? If I miss the first part, then what happened? It's 0. Okay, it's 0. And then first 5 elements. What is the stop? Stop is 5 I mentioned. Okay, I've not mentioned the step part, isn't it? If you want, you can see using X. I just miss all of them. Then what happened? It considers the by default 0 and then total elements 10 and then step is 1. This is equivalent to this. X of 0, comma 10, comma 1. So not comma, sorry. 10, 1. What does it mean? This is inclusive. Start is always inclusive. Stop is always exclusive. I mean to say, there is no such nth location, but there are locations only up to n-1. That's up to 9. Right? Yeah. Okay. So now only first 5 elements as a subarray. If you want, you can just. So otherwise, I just wanted to start from the 5th, that's the 6th element, and then followed by 6th element means what? 0 to 4 is 5 elements, and 5 starts at the 6th position. No. Okay. So that's what 6th position to n-1. And if you wanted to extract in between the 4 to 5 positions, 4 is included. I mean, 5th one is included. Okay. And then up to 7. So 4, 5, and 6. Okay, are extracted. And then step, I did not mention what is a start and what is stop, but I mentioned step. Every another element, skipping one element. Okay, so that's what it starts at 0 and goes up to 9, but now ignoring 1. So because the step is 2. So every other element. And then similar to that, if I start at 1, then it takes the every other element from 1. Right? So you have to practice a lot on these things to understand better. Right? You have to change, you have to, first you have to fix what particular subarray you wanted to extract, and then define your index positions into these signature, into this signature. So all elements in reverse order, as I told you, native indexing is also possible, right? So you can give like this. If I give -1, what happen? All the elements starts at the end and proceed towards the beginning. But the biggest thing here, what happened? So in this case, start is treated as a stop, or stop is treated as a start. Understand? So that's how it reverses. Now let us look at multidimensional subarrays. Multidimensional sizes works in the same way, and the logic is same. But the one what happened? Multiple slice separations by comma. Okay, as it increases, the dimension increases, then you will just separate them with the commas. First part is for the first dimension, second part is for the second dimension. If I have two-dimensional, then first part indicates the rows, and then second part indicates the columns. Here my x2 is this, okay, and then what I do is I'll simply take x2 and then yeah. Now you observe what happened. This is actually nothing, right? As it is. Now you observe x2. Okay. Now this indicates what? This indicates what? Row. This indicates what? Column. So when I have two dimension, this is the first dimension. This is the next dimension. Right? If you want to start at this one. Now you tell me only 70. It for suppose I wanted to columns start at only 2, 3. So now you see. It's very simple you to create a sub arrays using indexing and slicing. Index and slicing are powerful mechanism for you to extract the sub arrays from the arrays at any dimension. Okay. Now you can just simply, so you can just play like this. You can also put them in a reverse order as you require. If I mention minus will not happen, or the last row comes first, okay, and then follow and go on. And then if I mention this, what happened? The last column becomes the first column, right? First you just see x2. Now this is your x2, no? Now what you do is x2. I just wanted to put this only. Now you observe. Now my rows are reversed. First row become a first, last row become a first row. Right? Similar to that, if I wanted to put my columns in a reverse order, I'll do this. Now you see the column, last column becomes the first column and so on. Right? Then first becomes the last one. So like this, you can easily uh, rearrange them, and also you can extract the subarrays. Right? So, yeah. So the no copy view is also little important. One important and extremely useful thing to know about the array slice is that the returns the views rather than copies of the arrays data. Okay, when you generate this using an indexing and slicing, you'll just get an output. Right, this is usually stored in a buffer. It is not permanently available. So views are like your views in the databases, and then they are just for displaying on the interfaces or the echo, where people can just see. Next time when you wanted to see what is being displayed, it will not be available, right? Because that display memory will be overlapped with the other display, isn't it? But if you wanted to save them for future uses, you have to store them in a memory location by creating copy. So copy will create a memory, and whereas views will not. So if I see, this is my simple x2, and then if I wanted to extract 2 into 2 subarray, then what you can do is this is my slicing and indexing to extract my subarray of size 2 into 2. But actually now you can observe whatever I have been extracted or created in a subarray, that is been stored into another variable, which is a copy. So this can be simply achieved using a function called copy function. Now you can observe here. So directly there it created a view. That view is stored into a variable. Instead of that, if I say copy, this copy will be created, and then you have to mention where to store, isn't it? I just told. Now if I print this, I'll get this. If you want, you can see your x2 also. Okay. When when you are using two uh, objects to be displayed, you have to use a by print. All right. Yeah. So you will just use reshaping. When you are one dimensional, you always want it to convert into two dimensional. You can easily do that by reshaping the arrays using a function called reshape. So you have to provide the grid size. The grid is nothing but the array you wanted to create. So I have elements from 1 to 10, the 9 elements, and I want to rearrange them into uh, two-dimensional matrix 3 into 3. So what I did is simply I just uh, created an array, and that array is rearranged into two-dimensional array with a function, universal function called as a reshape. All right, now you can observe. The first one is one dimensional. Now I just rearranged them into. So you have to be very careful when you are regenerating like this. The number of elements that you are arranging must match with the number of elements into your defined grid or shape. That's very much important. For suppose if I use 5. Now tell me what happened. It is unable to find the 3 into 5, totally 15 elements, whereas your range generates only values from 1 to 9, right? So I said upper is excluded. It created only 1 to 9, but you are looking for 15 values, you have only 9 values. Got my point? For suppose if I give 2, lower one, what happened? Now you see you have actually 9 elements, but you are trying to arrange them into 3 into 2 is a 6, which is also not possible. So you have to be very careful when you are reshaping the sizes. The number of elements available must match with the size of a new shape. This is an essential point to be remembered. And not only that, when you are reshaping is okay, you can also mention the axis, additional axis. If I wanted to create a 2-dimensional and then 3-dimensional and 4-dimensional, you can mention which dimension you want. Okay, so another common reshaping practice, and that pattern is the conversion of one-dimensional array into two-dimensional row or column matrix. This can be also done with the reshape method or more easily done by making use of new axis attribute along with the slides. Now you can see how we can do this. Now if I use it, now you can see what I did is my simple one is converted into 1 row and 3 elements. Right? Now what I did is np.new axis. Now you can see when I say new axis is added, Now first one is, see, you all know when I separated this in the slicing, if I separate the slicing with the comma, the first one become a row, second one become a column. All right. New axis is a row now. Similarly, if I use it in another part, then it becomes a row axis. Sorry, column axis. Right? Now you see now. If I use this new access in a column part, then it becomes a column matrix. You all know row matrix and column matrix. Row matrix contains only the one row and multiple columns, and column matrix will have only one column and multiple rows. Got it? Now let us also see the concatenation splitting. Of course, we have seen the bit of concatenation in our previous discussion. In addition to it, it is not limited to single dimensional. It is you can also apply the concatenation and splitting concept on multi-dimensional using universal functions. You have two other concepts called as vertical stack and then horizontal stack. You can explicitly mention how you want it to concatenate. So whether it's a concatenation or simply called as a joining of any two arrays using universal functions called concatenate, vstack or hstack is simple in NumPy. Now you can see, let us see a few examples and then we'll conclude. Now you can observe here, I've got two arrays. One-dimensional arrays is x is 1, 2, 3, and my y is 3, 2, 1. And then I just wanted to concatenate. As I told you, the concatenate, you can also mention axis, right? Axis equal to 0. Now tell me what happened. Now if I give axis is 0, it is the same. Okay, it is the same. For suppose if I give axis is 1, what happened? All right, it is supposed to go the row wise. Okay, now you observe this my simple concatenated two elements. You can also concatenate more than two arrays at one go. I have created one more with an elements 99 3 times, and then I added one. So like that you can concatenate any number of arrays at one go. Now let's apply this on two-dimensional array. I've got now the grid 1 and grid 2. Grid 1, grid 2 are the two arrays. Nine and so now what I want to do is I just wanted to concatenate grid 1 and grid 2. All right. Grid 1 and grid 2, grid 1 and grid 2. Right. What is the error? Grid 1 is not defined. Where is grid 1? Grid 1. Yeah, so grid 1 is defined. Okay. Grid 2 is also defined. Right. When I concatenate, now you can see this way. Grid 1, that's the first array, and then this is the second array. Right, it's concatenated perfect. Now let us also give access, as I said. Right, as I said, the access 0 is a row wise, access 1 is a column wise. So then access 0, if I give, what happened is the same. It is the same. Okay, grid 1 and grid 2 is an alternate. By default, it's a row wise. Okay, now if I wanted to do it on column wise, you can do it. So this is a column wise concatenation. So for working with arrays of mixed dimension, it can be clearer to use the vertical stack and horizontal stack. Now what I do is simply I just create a one dimensional, because as I told you, when there are mixed dimensions, one array is in a one dimension, other array is a two dimensional. Then when I wanted to concatenate them on a different dimensions, then we will use two universal functions called vstack and head stack. Now, if you see this axis 1, 2, 3, whereas grid is this 2-dimensional, I just wanted to add them vertically. So now you can observe concatenated vertically. Vertically means what? Okay, this is row wise. Vertically means what? The row wise. Similarly, if I wanted to concatenate them horizontally, I have another array. I just wanted to add horizontally. That's what is column wise. Now you can see it's added as another column at the 9, 9. Okay. Right. So these are very simple. Concatenation can be applied on a similar dimension arrays. Could it be one dimension, 1 to 1 dimension, or 2-dimensional to 2-dimension, and so on. And whereas when the dimensions are different, still you wanted to concatenate, then you can use V stack, a vertical stack, that is a row wise concatenation, and head stack is a horizontal stack, that's a column wise concatenation achieved through these 3 universal functions. So similar to that, then you also have a D stack. D stacks means what? Along the third axis. If you have any third axis, you can simply use. So coming to the splitting, concatenation is anyhow joining, the splitting is dividing, right? As simple as that. The opposite of concatenation is splitting, which is implemented by using a function called split. So opposite to your concatenation is a split, opposite to a stack. A stack is V stack is a head split, and then head stack is V split. For each of these, we can pass the list of indices given. Exactly the splitting point where you wanted to divide. Now you can see I have a matrix 1-dimensional array. This is my 1-dimensional array. I just wanted to split them into 4 sub-arrays, right? 4 sub-arrays. So now X is first argument to split is a 1-dimensional array, and 3 up to 3 is a one part, right? Up to 5 is the second part, up to 7 is a third part, and so on. So I mean to say 3 always 0, 1, 2, right? 0, 1, 2 is one part. From 3, right? From 3, 3, 4 are the 2 elements, right? And 5 and 6 are the 2 elements. 5 and 6 positions, I mean to say, right? And then 7 is only one element, because totally how many elements you have? 0, 1, 2, 3, 4, 5, 6, 7, 8. 8 position, 8 elements are referred from 0 to n minus 1, that is 9 indexes. So the first part is, okay, first split happen up to 3, right? Second one up to 5 in 5th index, and then next one in there at the 7th index. That's what we'll get. Totally 4 arrays. We are storing them into 4 elements. Okay, now you can see we have got this. It's very simple. Similar to that, you can apply H split and E split. Now what? See, I have this 4 into 4 matrix array. Now I wanted to divide it into upper and lower matrices. Now you tell me carefully, V split. I'm passing this as an argument, the entire array is an argument, and now specifying how many you wanted to divide. Now, it's very much important for you to understand here. This is what is an upper. As I said, it is to be divided into two sub-arrays vertically, right? Vertically, I wanted to split. That's what I said. Head split is against to V stack. V split against to head stack, and split against to concatenate. That's what you have to be carefully understand. It's not the heads and V's must be same, but this must be opposite. That's what here we, if I use a V, you're trying to vertically split, but when they split it, they becomes a rows. They becomes rows. Next, similar to that, if you split like this, then what happened? Now they are divided into the column wise. 0, 1. The first two are divided into one column. The second two are divided into the other column. So head split is actually opposite to V. Very much important. I suggest you all to go for thorough practice. Then only you will be able to understand and then help yourself. So thank you all. We'll see in the next session.